Over the past couple of weeks, we talked about atoms and the structure, electronic properties, and we've led up to this idea of molecules. And so where we're going to wrap up this semester is looking at the properties of individual atoms and basically using the periodic table as a guide for these properties. We've already started on this. We've already been able to look at the periodic table, and from the location of items on the periodic table, we can predict the electronic structure. So we can look at nitrogen, and we can say that it is a 1s2, 2s2, 2p3. And with that is a host of other properties. We know that it will most likely ionize to form an N-3 ion. We know from its location on the periodic table that it's a non-metal. We know what its molecular weight is. We know how many protons it has, 7. We know how many electrons it has when it's neutral, 7. We can even say where those electrons are within the atom at various energy levels. So a lot of this information there stored right on the periodic table. So very powerful tool. And today we're going to add a few more things to it. So how did this periodic table develop? Now the periodic table, back in the late 1800s, so there was probably only about 25 elements known. More or less, so right around the 1800s, about 25 different elements. They weren't even sure what elements were, like what makes an element, and so they just knew that they couldn't break them down anymore. And there were several attempts to try and codify this understanding, but with 25, it's a little bit hard. There wasn't any obvious trends. Right around the 1850s, people started to recognize that, well, we can start to arrange these based upon weights. And so we can arrange them by weight, hydrogen, lithium, sodium, etc. We could arrange them by weight and look at their properties as a function of weight. Some of the work that was done was like this little spiral that relates the weight of a compound to its properties. But it wasn't until about 1864 that the real work was done. They started to recognize things like sort of this law of triads, where you could look at something like fluorine, chlorine, and bromine, and recognize that these three elements had similar properties, and so they started to find these little families, these little groupings of atoms. And one of the side effects was that the element in the middle had properties intermediate between the elements on either side, and so this sort of average properties. And so from that, they could start to make assessments upon it. And they could predict some simple work. The trouble is the law of triads started to break down, and the groupings weren't always neat. Right about 1863, a guy named John Newlands, came up with this idea of, he recognized that if he lined out the properties of an element, every 8th element had similar family of properties. So he would look at lithium to sodium, and they started to develop this relationship. Every 8th element would have this reproducible set of properties. And he called it the law of octaves, and making this analogy with music. And of course, everybody laughed at him because this is like music and elements. Oh, that's crap, all right. But it turns out he was actually pretty close, and he was almost this close. So this Russian chemist, Mendeleev, took this idea of the law of triads and this octave analysis, and he started to develop his own periodic table. And one of the things that he looked at was how the elements formed compounds. And so what Mendeleev did is he looked at how they react. And so some compounds formed groups of elements with oxides, sodium and lithium, could both form oxides of that formula, whereas magnesium compounds would form oxides of MgO, a single oxygen. And he started to group these based upon their properties and how they reacted with various other elements to develop a sort of another similar classification. And he sorted them also by weight. And he could see that a fair number of these compounds fell within categories of similar trends in size and behavior. And where Mendeleev got his claim to fame, and why we often classify Mendeleev as the father of the periodic table, is that he predicted that there would be other elements under aluminum and silicon that had particular masses and the specific properties. You could actually predict density and other properties from this. And and those predictions were spot on. I mean, this is scientific method in action. Right? You have a hypothesis, and you predict what the answer to your hypothesis is, and if it fits, then you know you're in good company. So this is how the periodic table grew. And there was other work being done, particularly with the atomic number, looking at alpha particles and alpha scattering. If you take an alpha particle and it's scattering, from its scattering you can predict Z, the atomic number, and that actually clarified many discrepancies in the periodic table and led to the ability to if we know atomic numbers, we could actually find significant holes in the periodic table that could then be filled. Right? So by arranging these by atomic number, we got a much clearer picture. And then we eventually developed this electronic structure model, which we've talked about in the past, and grew into this modern periodic table that we are used to seeing. Right? So this is the periodic table. What else can it tell us? It turns out that the periodic table is a treasure trove of information. And we're going to talk about three distinct properties, three distinct items that the periodic table tells us. Okay? Those three things are the ionization, the size of the atoms. We can predict relative size, something called the ionization energy, and lastly, something called the electron affinity. So all of these relate to fundamental properties of the elements. And what we see is, as the name implies, these are periodic properties. They repeat every so many atoms. The rows are called periods. So going across the periodic table, this is called a period. And within a column, these are called families. And we've already looked at the names of four of these families. We have the alkali metals, the alkali earth metals, we have the noble gases, and we have the halogens. And those are our four of the named families. These are actually called the chalcogens and the pycnogens. These are transition metals. These are the lanthanides. And these are the actinides. The only four you really should concern yourself with are the alkali metals, alkali earth metals, halogens, and the noble gases. But these families, each is represented within a period. So we have these periods that go across, and then what happens is the whole thing resets itself in the next period, such that the behaviors, a monovalent cation, a divalent cation, repeats, trivalent cation, something that forms a -4 or a +4 depending, -3, -2, -1. Materials that are more likely to be gases, materials that are more likely to form divalent anions, things like that. So the properties cycle every single time through a period. and then you move to the next period, and then you move to the next period. And there are deviations, that's given, but for the most part, these trends periodically reproduce themselves, and we're going to talk about those.